All right, I think we can get started. I think the crowd kind of dwindled, but that's okay. I mean, we started at 1:30, and that's how it goes. But yeah, thank you for being here, and thank you for all the speakers, panelists to be here. So I just wanted, the panel to just go around with a quick intro from each of you on your work. Brendan and Yatin, even though you spoke, it's still a very small, microcosm of what you do. So in the context of the theme of this meeting, which is, action at the intersection of these disciplines, right? So if we can talk about your interests and, what you do, I think that'll set up the questioning round. So maybe Brendan, you can get started, yeah.
Yeah, sure. So I'm Brendan Kochunas. I'm an assistant professor in the Nuclear Engineering and Radiological Sciences Department. My training is entirely in nuclear engineering, but a lot of that has involved computational simulation. So I have sort of a earned experience there.
Hi, Yatin Manerkar, assistant professor in the CSE division, and my research lies at the boundary of formal methods and systems, and the systems are largely computer architecture, but not entirely. And a lot of my work is developing automated formal methodologies and tools similar to the stuff you saw for the design and verification of computing systems, particularly for concurrency and hardware security.
Hi, my name is Mosharaf Chowdhury. I'm an associate professor in CSE. My research focuses on building very large-scale systems. More recently, we are focusing on building systems for AI and ML, ranging from sort of the entire life cycle of it, training, tuning, inference, but specific focus has been on energy optimization for AI, especially with the rising size of the model, each of the model to train, to infer, they consume a lot of energy. And my group and I together, we are leading the ML Energy Initiative, where we are trying to understand and optimize energy consumption of AI throughout the entire life cycle.
Hello, everyone. I'm Gokul Ravi. I'm also in the CSE department. I'm an assistant professor. I work in the area of quantum computing. So my background actually was in classical computing before I got into quantum. So my research usually is sort of at the interaction of quantum and classical in different types of ways. So some of my work is in software, building software and compilers to improve the quality of application execution on quantum devices, like managing errors and noise, which are pretty challenging things to deal with in quantum. I also work on building classical hardware, basically components which sit close to the quantum device and have to constantly interact with them. So I try to optimize them to make them more efficient and thereby make the quantum computers more efficient as well. Then I also work on things like resource management, which involves both efficient use of the quantum devices as well as these classical resources, which can also be sometimes have pretty high computational costs. And overall, I know the theme of this symposium is, I think it was advanced algorithms, HPC, and AI. And I think quantum plays a key role in interacting with all of these. I think maybe over the course of this panel, I'd be happy to talk about each of these and at least my thoughts on it.
Okay,
Thank
great.
you.
Yeah, so the way we're going to go through the panel is first I'll ask one general question to all of the audience, to all of the panelists. I'll open up to the audience, and then I'll come back and then have specific questions, right? We'll go that way. So the general question I have is, first, in your specific disciplines, right? All of the work you're doing and what you spoke about today is exciting, right? For instance, Yatin is thinking about hardware, software, co-design. Brendan's thinking about synthesis. And, you have quantum, and then you have, federated learning, energy-aware AI. So I want you to, each of you, in your particular problems, to talk about what is the biggest bottleneck, right, in taking this to the field, right? The field, in this case, maybe the field can be scientific computing. So, Brendan, in your case, you looked at program synthesis. You've thought about it for a year. You kind of explored the space. There are obviously many things we can do, many papers we can publish, for the next 10 years. But still, when push comes to shove, what is the biggest bottleneck that is, And I think the same question to all of you in your particular disciplines, right? For instance, Yatin, I want you to tell us, even in your classical problem spaces, there are some bottlenecks. Some people will be, this doesn't work, that kind of thing. But then when you translate it to real world scientific computing, what are some of the challenges, right? It applies to all four of your things. Yeah.
So I would say the main bottleneck is under really understanding all of the subtle detail in sort of the expert algorithms. There's just a tremendous amount of knowledge there that it takes time to learn if you haven't done it before. And that has to exist kind of in a few minds to be able to put it into sort of an automated algorithm. It has to be very well intuitively understood. So for me, that's the bottleneck.
Yeah. So if I may press on that, right? So I don't consider that as a bottleneck. Just hear me out, right? If you can guarantee me that this is going to run 4 times faster, right? Anybody is going to invest. But do you see that kind of thing coming from modern program synthesis?
From what I know about modern program synthesis, yes, but I don't think it'll be quick. So the other thing I've learned is, the scope of code that can be synthesized is actually quite small. And so, think tens of lines of code.
Yeah.
And so to be able to scale that up to hundreds or thousands of lines of code is going to probably require a few different kinds of technologies.
Okay, thank you. Yeah, so Yatin, so maybe pressing challenges in your own classical problem spaces, and then maybe the scientific computing to whatever extent you can relate. Yeah.
Yeah, so I would say the biggest challenge on formal methods work tends to be scalability, because if you're doing a automated proof approach, then often the SAT and SMT solvers that you use, the runtime or the memory usage tends to blow up because they are NP complete or NP hard. And so that tends to be the thing that gets in the way the most, because it doesn't take a lot for you to create a model that is going to take an egregious amount of time to be verified. Yeah. And we have to be, it's somewhat of an art. You have to be very careful and smart about how you encode the problem in order to get things to work. And I see potentially similar things occurring in the scientific computing space, because as we move forward to do things like co-design and have more and more complexity in order to eke out more and more performance, which we need to do given the workloads that are involved, I imagine the system models are going to be more and more complex, and this is going to feed into the runtime even further. So trying to get that to scale is also going to be challenging, possibly in some respects more so than for traditional computing systems.
Okay, yeah, thank you. That's good insight. And Mosharaf, this question would be harder for you to answer because I feel some of the things you do can directly help. But anyway, what are some of the biggest bottlenecks?
Yeah, so I'm going to sort of take a very broad view of when you say bottleneck. First of all, I want to mention that power and energy are they are very related. So you can say almost the same thing, but they are not. It is the most important problem that we have today. Even if we have infinite money, we cannot deliver enough power to build up the data center and supercomputer we want to build, which actually led to our work on how to reduce energy consumption. Given whatever power we have, how can we run more? And the other part is, which is also going to lead to a lot of federated learning research, because you cannot have all the power in the same place. They will be in different supercomputers and data centers, and you will have to run across the geo-distributed sort of compute. Said that, in terms of bottleneck of how much can we do, there are, again, I'm going to split it. One is bottleneck in terms of the algorithms that we have proposed, how well can they run? The problem we face is how good of a support existing hardware or the future hardware provide in terms of measurement and control, sensing and actuation. So the hardware that we have, the energy counters they provide, they are very coarse today. You can probably poll at every 100 millisecond. So you cannot do very fine-grained measurement unless your computation is large enough. The other part is, even if you know what to do and you ask the hardware to do something, they are very slow in reacting. So there is a lot of research that I am like software person, so the hardware folks need to figure out how to do it sort of faster and at a more finer granularity. And however much we could gain, say for example, for GPT 375 billion, we have shown that you can reduce energy consumption without any slowdown for the same model on the same hardware by 25 to 30% using our algorithm, which is massive when you think about it's like they take tens of gigawatt hours to train. The problem we face is that the cloud is the problem. The cloud is the problem in the sense that the pricing model of cloud, this is the deployment bottleneck. Pricing model of the cloud hides everything under like $1 amount, and the cloud tenants have no incentive to try to use it, because whether you save energy or not save energy, you will pay the same amount. The cloud providers and the people who build supercomputers, they are the ones, like people who pay their own electricity bill directly, they are the only ones who would want to use our sort of innovations. As you said, that, okay, if I save 30% and save $3 million a year, are you going to use it? There are not too many people in the world who has that problem. Everybody else is, if I save energy as a cloud tenant, I will be making more money for a cloud provider and nothing for me. So no one has incentive. But it's an easy problem for the supercomputing folks. DOEs will run national labs because they pay their own bill and it's not lent out to sort of outsiders. So I think it's that bottleneck doesn't exist in that world. So yeah, overall, bottlenecks in research, bottlenecks in how far you can push, and also bottlenecks in actually getting it out there. There are a variety of things. Hopefully one of or two of them answered what you were looking for.
Fantastic. Yeah.
Okay, so I think I'll talk about three kinds of bottlenecks. One of them is sort of the macroscopic one at the like R&D level for quantum. One is the same thing but at a microscopic level, and the other one is sort of a meta bottleneck in terms of workforce and education, right? So the macroscopic bottleneck, which quantum needs to overcome, is that there is this huge gap between theory and experiment, right? So there has been quantum theory for now since almost like 40 years. So since the early 80s, there has been some theory, and then of course in the 90s there were like these. So the stuff in the 80s was more about like how for scientific computing especially, so how some of those problems are clearly suitable for quantum because they have some exponential hardness to them because of like these many body systems and so on. Then in the 90s we came up with like classical algorithms for which we could use like quantum computing to accelerate them, and there have been some more discoveries like that in the 2000s and beyond, right? So but since the I'll say the late 90s, early 2000s, we have had some form of qubits. So we have had devices. In fact, some of the early work was from Michigan when Chris Monroe was here in the early 2000s. So I think the first ion trapped or qubit was probably from his group. Yeah. So, but though these two have therefore existed, we have had experimental qubits and the quantum theory, there is a very significant gap between the kind of idealized qubits which theory needs for us to achieve quantum advantage and what qubits are really doing, right? So in theory, they do have the ability to give this exponential kind of benefit, but they are affected significantly by noise and so on. So the whole like research agenda for the entire community over the past 10 plus years especially has been about bridging this gap, right? And we have made tremendous strides in this, and this is why in like 2017, 18, like IBM had like this 4 qubit, 5 qubit machines, and now they're at 1,000 qubits, and we are starting to do useful stuff with them, right? They're in no way right now competing with state-of-the-art classical HPC systems, but at least we are at the point where there is a back and forth between the two communities. So the quantum says that we can beat you, and the classical proves them otherwise, right? Even the fact that we are here is a tremendous achievement. Now, taking that to the microscopic level, I would say that the challenge is errors, right? So qubits are extremely noisy. A transistor in the classical world errors, I think, once in 2 to the power 20 years or something. I mean, don't quote me on that, but it's something like this, right? So, of course, you still get errors because you have so many transistors. On the other hand, a qubit today errors once in like every 100 to 1,000 operations. And so of course, there is clearly like no equivalence over here. And even 10 years from now, we don't expect qubits to maybe improve by more than an order of magnitude. But in reality, for some of these quantum applications, we need error rates like 10 to the power minus 15 and so on. So there is this huge question of how exactly we achieve this, right? So, of course, this doesn't mean it's only at the physics world where you try to improve your qubits. There is amazing research in quantum error correction theory and so on, building more noise-resistant algorithms. But again, a lot of research is needed in this sort of microscopic space in terms of how can we overcome errors and thereby truly capture the advantage of quantum computing. The final one I want to mention is not really related to research. It's more about how people get into the community, right? This is also a huge bottleneck because a lot of people assume that in order to work in quantum computing, you have to come from you have to be trained in the physics and math of quantum, just because there is, of course, like 100 years of research you can think about in terms of like learning quantum mechanics and so on. So, and therefore this is often a significant barrier, but I would like to like strongly state that this is not a requirement to really work in. Of course, there are areas of quantum where if you're a physicist or even if you're working in theory where you need to come from a math background, if you're a physicist working on qubits, you need to understand the physics of the qubit. But there are many other areas, for example, in terms of software design, building the system stack, building classical peripherals and so on, or in some sense, all the kind of research that I work on where you don't have to come from a math or physics background because I did not, right? So, so I think there are a lot of opportunities, but I think there's still an ongoing effort to overcome these challenges.
Yeah, thank you. Fantastic insights. Okay, we'll do a round with the audience and then I come back. So any questions for our panel here on anything that, they spoke about just now or anything that you heard from, the other speakers?
So I'll revisit. There's nothing like the human brain, right? And the ability to, I guess assume people can't hear, right? So I'll go back to my question before about, the human brain and the mass numbers of people involved in a project, right? And where do you see that behavior or the way the humans work, right, in problem solving, iterative experimentation, trying things out, dreaming up something, right, and then see what it does? In each of your areas, how do you see that fitting in? Because I think it's going to be crucial in AI, quantum, that those things have the ability to do that sort of thing.
That's a great question. I'll punish all of you by having all of you answer that. No, but it's a very good question. I mean, that's a bottleneck, right? Yeah.
Could you repeat the question?
Scaling. In the end, it's people who do.
Right.
Yeah.
It's the mass numbers of people involved, and it's the iterative trial and error, and just to try things out, right? And it's a dead end, right? The IBM computer, game thing, right? That's how it exceeded, right? It played chess, it did a move, and then had the ability to experiment. What are all the counter moves and what are all the moves that I would have done and blah, blah, blah. It blew away a human being, right? But a lot of problems don't have that, are amenable to that sort of thing, I think.
And anything that's amenable it will be beat by quantum computers because they're good at searching. But yeah.
Well, so I guess in the stuff I talked about, I feel, fortunate that, we have already a lot of the known solutions, of like what the high performance algorithm is. We just want to simplify the process of making that available to programmers, without all of having to go through the process of learning everything you need to learn to be able to do that yourself. So I guess I see that, right. We know what the right answer is. That's a huge upside. In other cases, we don't know what it is. We're just trying to figure out how to, represent the thinking to get to these right answers.
Yeah. And I think, Gokul, you may have a particular perspective on that as well, right? So not all four don't have to answer, but I think Gokul may have a,
So, so I don't necessarily have a quantum specific perspective, but I will give my opinion of an emerging technology perspective to your question, right? So I think one of the challenges with any emerging technology is that, especially in a technology where it's almost there are so many unknowns at every layer. So that's how I kind of interpret your question, that we have like a bunch of folks working in all of these different layers, all trying to innovate. It's like, how does it all come together truly into like a moment of singularity or an inflection point where it actually starts to mean something and become beneficial, right? So I think, so there are always goals which you can strive to achieve, because, for example, like I said, there have been like this theoretical work in the past. So there are some known like theoretical algorithms which already exist, which have been invented. So now the other folks like down the so I sort of look at theory in the top, then you have like the software and computer architecture and systems folks for quantum, and then you have like the circuit designers, the quantum circuit designers, the physicists, and so on. So in some sense, everyone is looking up. So we have the theorists who come up with like the first theories and so on, and we know that, they know that there's some algorithms which can have this benefit. So now we are all trying to work towards trying to make our contributions so that we can hit some threshold where it becomes meaningful for that theory, right? So now what the theorists are trying to do is actually trying to push that threshold down, right? Because the earliest theory might have assumed that, okay, all of these things have to be perfect, only then can we get quantum advantage, right? But now they're, the new theories and new applications are being proposed where they're trying to say that, oh, it's okay if things are not perfect, maybe there is still quantum advantage, right? So in some sense, everyone is working, even though people are from very different fields, like the theorists are like hardcore math folks, the physicists are the experimentalists are physicists, and there are other folks like me in the middle in CSE and folks in ECE. But we all have a bunch of metrics which we are looking at, and which of course varies across these layers, but there are some defined metrics which we are all looking to push our own research towards, so that at the end, we know that if we hit this metric, this is going to be useful to the next layer. And at some point, if everybody is hitting these metrics, that's when the full stack becomes useful, and then you reach that inflection point, right? So I do think this is a challenge. And this goes back to my point that about the education aspect of it. So I spoke about this in the context of getting into the field, right? So like if you don't have a math or physics background, but I think it's also the case that if you're sort of working in these specific areas, which are in some sense, because it's sort of new and it's so niche, you don't necessarily know what the other person is looking for, like what the theorist is looking for from your results. And it happens a lot. So I have been to like some quantum theory conferences, and they don't recognize like what exactly you're doing or why it would be useful to them, right? But so I think it's up to the entire community to realize that their research alone is insufficient and try to work together in these metrics.
Okay, yeah. So Mosharaf,
Yeah, I just want to add a quick thing. The word that came up when he was describing it. I teach undergrad networking, and we focus on internet. Internet is the biggest system humans have ever built, and we use it like all the time. Right now we are using it. We never think about it. And it involves lots and lots of people. Like starting from very low-level hardware and going up to people designing websites and such, and everything in between, and architecture folks and software and theory. The reason sort of the internet exists and does so well so far and has been doing so far is because of the layered design. This layering sort of allows people, researchers in each layer, knowing that what are the interfaces they would use to interact with the people above and people below. And they just need to make sure whatever they do, the interface cannot change. and this is how much they can receive, and this is how much they can provide. And with that in mind, everyone can sort of independently explore and try things out. And whenever something is interface breaking, then it becomes a big problem. Then someone needs to think, is it big enough, like 4x or 40x improvement, that should lead to rethinking the interface? And that's why it sort of moves very slowly. But this decoupling of layers also allowed, like something like internet, this gigantic beast connecting, like at this point, maybe trillion devices working together so well. And I think for any technology as it emerges, as he was saying, that it's sort of having layering allows us to innovate quickly.
Right. All right. Other questions? Yeah, go ahead. Just one sec. The mic. Yeah.
I can talk louder. Okay, I agree that quantum is very up in the air or down on the ground, whatever, right now. And I know that a lot of things cannot be solved faster in quantum than in classical. I mean, I've published 100. But what quantum does seem to do very well is approximate solutions. Okay, and when that handles noise and all this stuff about spin up and so on. Unfortunately, the persistent calculation person isn't here. So can science use more of the inexact calculations? And how can we do that? Some of you say no, because you're doing exact.
Well, I think the inexact, it depends on at the what level, right? So I think in the context of their work, I think it's more about you still want guarantees that the inexact solution, again, I don't want to speak for them, but in general, you are okay with some amount of error in some applications as long as it is still, you need to ensure that the culmination of errors across the entire course of your execution is still within some tolerable error bound, right? So for example, in chemistry, we have this notion of chemical accuracy where only if you're like calculating what we call the ground state of a molecule. So if you're calculating the energy, you're calculating this at like different like bond lengths, and then you're using this to like find some information about like a chemical reaction rate or something, right? So, but only if you're calculating each of those within some amount of accuracy can you therefore make some reasonable estimates about the chemical reaction rate, right? So yes, it is the case that there are applications, especially for scientific applications, where you're not looking for one correct answer, or in the sense that it's okay if you have some error, but you still want in this case, all your qubits to have like error rates low enough that even the combination of all these errors, because you might be executing like 1 million to 1 billion gates for complex applications, right? So at the end of that, you still want your errors to be within a particular bound, right? There is also the case that even for applications where you actually need one single correct answer, it might also be that verifying them might be something you can do in polynomial time. So of course, even if you run that iteratively, find a bunch of answers. So yeah, so there are these kind of things which are possible. And which is why like material science and chemistry, physics problems in general, there are a lot of problems that, so I'm not specifically an applications person, but we do look at a lot of applications where there is some tolerable error. But I would just say that right now we can solve like toy versions of those problems with excellent accuracy, but we aren't yet at the point where we can solve like real world large scale applications, right? But hopefully we will get there in the next decade.
Yeah, and I can say in pretty much any physics, scientific computing problem, if there is the ability to estimate or bound the error,
right,
then 100% it's going to be useful, right? Any context. And, the Blackwell is supposed to be exaflop on a chip, but at FP4 or something. So all right. Other questions from the audience? Go ahead.
Test. Okay. So it occurs to me that when we design some systems or when we try to automatically synthesize some programs, would it be worthwhile to consider the ease to verify or test the program or the design system when we design or synthesize it, or it is better done post hoc? That's the question.
I think that's a question for that side of the panel.
So yes, design for verifiability is something definitely worth considering. The irony is that a lot of the complexity in our systems and the need for formal verification in order to ensure the system is correct come from the fact that we design for performance. And performance tends to be the single biggest factor in combination with energy efficiency, as Mosharaf was saying these days. But a lot of the issues that we run into are because we make our system so complex in order to eke out as much performance as we can or make sure that we are as energy efficient as we can. There has been work that looks at design for verifiability, and I can think of some in the context of cache coherence protocols. And it can definitely have benefits, but the flip side is that trying to get the industry to build devices along those lines can be tricky because it is not going to be as beneficial to their bottom line as if it were something that perhaps is more performant but still more complex. When you have bugs that cause, say, issues with the hardware, that can significantly impact the bottom line of a company negatively. And for instance, when the FDIV floating point bug happened back in the 90s with Intel, that actually caused them enough pain that they invested a significant amount of money in formal verification as a result. So the benefits of kind of design for verifiability or even just using formal methods in general are more, for lack of a better term, implicit than they are explicit, in the sense that it's difficult to measure what they gain you because they succeed by having bad things not happen.
Yeah, I'll kind of add to that. Yeah, I think to add to Yatin's remarks, this notion of verifiability. So I'm coming at this kind of strictly from the software side and algorithms. Like, if you, what I try to teach a lot is if you don't have an expectation for what the right answer is or what the answer should be, like you should just stop at that point and work on that. Like you don't want to you don't make a lot of progress in research by throwing darts at a wall because you're not sure what the right answer is. You should really sit and think about the problem. I tell students, like, I don't expect you to be able to solve your problem on a supercomputer if you can't first solve it with pencil and paper. Like you have to have an expectation for the answer. And that expectation of what the answer should be is like essentially what you verify against. And there's formal ways of doing it in software. Testing is the main thing we do.
Okay, great. Other questions from the audience? All right, so I think again my standard question to all of you. Oh, there's one more. Sorry.
Online.
Yeah, please. Yeah, just hold on one sec. We are getting to the comments on Zoom. Yeah.
If I take Brendan's talk and combine it with Venka's talk from earlier today, it seems like you have defined a perfect, in quotation marks, application of machine learning-based program synthesis in these linear algebra algorithms. It is extremely easy to check if algorithm compiles, to check if it produces the correct answer, and to measure the speed. Okay. Okay, can you wrap up? Okay, can you wrap up a synthesis model with some additional AI tool like Venkat was trying to describe with the direction to search for new, better algorithms to the particular end of program execution speed? Do you see value in trying to see if it's possible to approach the expert solution, in quotation marks, via that sort of approach? This was from Chad Mayer.
Yeah, so this is a great question. This is something I didn't talk about, but it's something we've thought about. The way I talked about what we were trying to do today was sort of a very limited set of examples of sort of naive programs and expert programs, and using that essentially as in a very general sense, the training set for the synthesis tool. But there's an alternative philosophy that you don't need high quality training inputs output pairs. You can just sort of generate them naively and synthetically and randomly, and through this process of sort of learning that Venkat talked about, like converge to something that is useful. And I believe there's been some other work along those lines related to training a model to write like Python code that was surprisingly successful. They would just start with an early version of itself, randomly generating Python output, and then seeing if it compiled, and if just flag it as if it didn't compile, it was no good. If it did compile, mark it good, and then use it to do the next sort of epoch of training, and just keep repeating that process kind of in a fully automated way. That can be successful. And I've thought, like, is that just a better approach? I don't know. It's certainly a whole lot less effort intensive. And I guess I have a personal philosophy that you don't get great successes without putting in the effort. Like solving hard problems isn't an easy thing. I can't just expect.
No, but somebody else did all the hard work for you. So somebody did put in the effort, right, in developing that framework. Yeah, if I may, I think one interesting thing about this evolution of AI is, especially when in this particular case, you can verify, you can get a yes/no very quickly. You can measure efficiency, you can measure correctness because you know the answer. This is almost the perfect case for AI. If it gets wrong hypothesis, the penalty of getting a wrong hypothesis is 1 cent maybe, right? Not development, but inference cost. So I think it's a very good use case for AI compared to the actual things that Venkat spoke about. Those are harder.
Yeah.
But I think I'm not saying this is the best way to do it, but I think this is a good use case. Yeah. Are there other online questions, or there was the one? Okay. All right. So I had, a few more elaborate questions, but I'm just going to ask, one question for all of you to bring your perspective. And I think, Brendan, you already kind of answered this part. I mean, I wanted to say, especially with introduction of AI and a few other recent tools, right? If each of you had done this work 10 years ago, right, compared to 2024, right? What is it that has happened in your field? I think AI is just one part of it, right? What is it that is making your work accelerate much faster? I mean, Brendan, I think in your case you would probably say AI. But is there anything else that has happened in algorithm? Is it because the exascale computing project put maybe 5 million lines of code? Is that, I'm just, yeah.
I don't know. Pass.
There's a lot of noise there. All right.
So on the subject of formal methods, I would say that it's a field where large improvements are actually not uncommon on the automated formal verification side. As in, if you see somebody present a form, so to contrast it, if you see someone give a computer architecture presentation, it's not unusual for them to say, if they didn't change the architecture massively, to say, all right, this was our baseline, we added these improvements, we saw 20-25% speed up, something like that.
Yeah.
Traditionally, that's been something that you see. And now if you have a specialized accelerator, you might see much more gain in the way of gains. But to contrast, in formal methods, if somebody says, oh, we had our initial approach that took 1,000 seconds, then we tweaked things, and now it runs in 100 seconds, you won't get very many raised eyebrows because that's actually not exceptionally uncommon. And so
you would get everyone except you in this room is going to have their minds blown, by the way.
and perhaps you as well, because I know you do formal methods as well.
Yeah, but yeah.
So the other thing I would say is that in the last 10 years or so, there have been advancements in the solvers we use for the automated verification. And there have been significant advances there. And every time people improve those solvers, then they impact a lot of verification workloads, usually in a positive way.
Yeah.
And so the improvements that we've seen in the past decade over things like the Z3 solver or CVC5, that's been quite beneficial. And AI has certainly helped as well, especially in the context of program synthesis, because it's one thing to define the space of possible solutions, and it's another to know where to look in that space.
Yep.
So for a while, the typical approach when you were doing synthesis was to just do enumerative synthesis, where you're just doing relatively a blind search over the space of possible solutions. But when you couple that with AI for generating possible solutions, it tends to be a lot better. It tends to be a lot better in the way of knowing where to look for likely solutions that you might find.
Okay. Yeah. Thank you.
So I build systems. So in our case, I think the biggest change in the last 10, even 20 years is the sort of scale. It used to be, you were doing things in one machine, then you go to, okay, it's a rack, it's a cluster. Now, then it became, entire cloud data center. And then we have gotten to the point where, as I was saying earlier, we don't have enough power. So we are going to run across multiple data centers.
And multiple continents.
Yeah, multiple continents potentially, and across tens of thousands of GPUs, like just to train one model. And that leads to a lot of heterogeneity. And then sort of both in terms of compute, but more so in terms of the communication network that connect all of these very far away resources. And as a result, sort of things that were simpler became much more complicated because you cannot synchronize so easily, and the timing problems are bigger and also more unpredictable, because when you're crossing the entire world, you can't really precisely say it's always going to be 100 plus minus 5 millisecond. You may be unlucky and it may be 200 millisecond, and that allows or that rather requires your systems to be more robust to high variations in terms of resource availability and communication delays. So all of those things made research in some way more exciting, like the problems are more challenging and bigger. That's how I would describe it. Yeah.
Good. Thanks.
Okay, so this is a bit of a tricky question for quantum, because 10 years ago we didn't have quantum computers like formally defined.
For you, it's 3 years.
Yeah, okay, sure. So no, I was going to modify that question a little bit. So I would say what has accelerated since quantum computers became a thing, which was like in the 2017-18 period. What are the things which have happened in the field which has accelerated research in the space, right? So I think one of the key things is how the quantum ecosystem has been designed, which I guess comes from many decades of learning from the classical world. Because if you see some of the main companies who are doing quantum are companies who have a big classical presence, right? Like IBM especially, and Google and so on. So the way they have designed these quantum computers, the ecosystem, the software, the open source access, their compilers, so many tools, has really enabled pretty much everyone so there is no way otherwise an academic, a student, or like anywhere around the world can do research in quantum, because they don't have access to quantum devices, right? So definitely the access to quantum devices and then simulators and all these tools has been instrumental. And I also think, like, in general, advancement in computational resources in terms of compute memory, like GPUs and so on, has all helped, because we also need to do classical simulation of quantum systems, right? That's how we verify that. Because if I need to run like 1,000 experiments before I can publish a paper, it's maybe only the last 10 or sometimes 100 of them which I can run on the actual quantum device. And those are often like some small scale quantum device which I get some minimal access to, right? So the first 990 experiments have to be run on a classical computer, which means, of course, I can't be testing on problems which are truly going to give me quantum advantage, because if so, I could not have run them on the classical computer to begin with. But at least I can use these toy problems, implement my methods, my compiler techniques. I can do like modeling of noise and so on, run it earlier on CPUs. Now we are, for example, through NVIDIA, we're running on like that H100 and so on, and we are able to produce quicker results, right? And I think these things are helping research progress faster in the field.
Okay, great, fantastic. All right, last round, audience, if there's any quick questions. Yeah, if not, thank you very much again for a really insightful panel. I'm glad we recorded it. There is quite a bit here. And again, I hope we get together, take some of these ideas, put it in a 4 or 5 pages, send it somewhere, and build research activity along the intersections of what we do. So Thank you so much for your time. And yeah, thank you for the audience for sticking around. And thank you for the people who joined online for your patience. Thank you very much again.